I'd like to introduce my colleague Prometheus Jasinski, who will take us through the topic of mid-distance presence detection. Prometheus is applications engineer, infrared detection at Excelitas Technologies, and best suited to explain what presence detection is and what you can do with such products. With this, I hand over to Prometheus and look forward to an introduction of the passive infrared sensors, which can operate without additional lens.
Hello, everybody. Thank you very much, Oliver. Good morning, good afternoon, good night, whatever applies to you. Today, we will be talking specifically about the CaliPile family itself. It's not just one detector, but it's a detector family, which was launched already quite some time ago, something like 2 or 3 years for mid-distance presence detection. And we are at the stage where the broad audience is really taking up this part. However, there are still many questions coming, especially from customers who are not experienced in infrared devices and are trying to jump over from active to passive sensors. This presentation, you have to understand, is a follow-up on 2 other presentations. One of them is the presence detection with ultra-low power infrared sensors. So if you would follow this link or look on our website, you can find also a recording of this presentation, which I strongly recommend to have a look inside, because there I'm discussing a little bit more the differences between the technologies which are on the market. You will find some of those slides also here in this presentation. I will just briefly summarize what I was talking in the other presentation, and I will discuss a little bit more the technical details on the CaliPile itself. First of all, I would like to clarify one important thing, which I would say almost always is the first topic to be discussed with the customer. What is actually presence detection? What is the understanding of presence detection? And I have to say that most of the answers which I get give me the impression that presence detection is just a buzzword. So there is this raises very often wrong expectations from a part, and it was very often abused by marketing. I'm at least not aware of many standards which are specifically talking about presence detection. So this can be regarded as a feature of a product, and the definition of it has to be understood in detail, not only for the solution of the CaliPile, but also for the solutions, for the other solutions on the market. So other buzzwords which I use more often are rather occupancy detection and motion detection. And all the 3 are somehow related with each other, which I will briefly touch. So I prefer to define the use case rather than just talking to the customers in terms of as a solution for presence detection. And in most cases, the customer is requiring to determine if a human is there, whatever there means. Of course, the wish to distinguish from non-human objects is very often a requirement, but sometimes also customers would like to see non-human objects. So this must be understood what should be identified and what not. Also important to understand is the area to be covered, since no sensor can cover everything, and with more distance, usually many drawbacks come. So you will see later in this presentation that actually, depending on the area which you would like to cover, there are different solutions on the market which might be more suitable than the CaliPile, and we are covering a very special area, meaning the mid-distance presence detection. Then typical patterns, are there observable? This eases a lot to help to improve the performance of a sensor. So not just saying, okay, I need to know whether a person is there is sufficient, but you should, for example, talk about the use case. I'm, for example, talking about an apartment with one room where you would like to see what the person is passing by. Or you would like to distinguish a person which is passing by from a person which is standing in front of the object. Would you like to of the sensor? Would you like to see the sensor, or should it be not visible, and so on and so forth? And at the end, there is always a trade-off between performance and reliability. Yeah. For one system, maybe less of a trade-off, for another system, a little bit more of a trade-off. So it must be understood, what is more important to the customer? Is it the reliability to detect absence or presence? Would you like, for example, to save on battery consumption, so then you don't want to have many false triggers? Or would you like to have, in any case, a very responsive system, which means it should rather light up even if there might be a condition which is not clearly the one defined. So let's jump a little bit into the technical solutions on the market, so just that we can compare at the end the solutions with each other. So presence detection is a quote which is quoted on the market. The state of the art, what I understand, can be subdivided into active sensors and passive sensors. Active sensors have always something like an emitter, which is emitting electromagnetic waves, light, radar, or even sound. So this one bounces off the object of the target, which you would like to identify, and then you have a receiver. This receiver has to look into the data which it is receiving in terms of time, amplitude, whatsoever. So let's have a look. What is possibly one solution would be the proximity sensor. Everybody knows the proximity sensor, which is a really nice solution for close proximity. Means if you want to identify, like in this example, if somebody is holding its phone close to his face, so that the buttons are being turned off, and you can save also on battery consumption because you can turn off the display. Such proximity sensors typically operate with an LED. I wrote here 960 nanometers, which is a typical wavelength, just to get it into perspective later on when we're talking about frequencies or about the range in which the light is being emitted. And then you have a feature which is optional. This might be a lens, and this lens helps you to gain some distance. On the other hand, with the lens, you will confine the field of view, which makes it not very broad visible, which makes it difficult to see people at large angles. And this data, which is being emitted with the LED, is then received by the photodiode. And at the end, you can measure the reflected intensity and you get the distance for this one. And in this case, you can regard something as presence detection only once you have seen motion. You are looking for a background subtracted signal. Give it, for example, the situation where you have your smartphone, take it outside, the sun is shining on top of it. So the sensor has to distinguish between this background of the sun, which is going on to the light of the photodiode, and then you can have a presence detection unless the background will change. Like, for example, you're going again into the darkness with this device close to your face. You can improve the situation by looking not only on the amplitude of the signal, but also on the time information. And there are solutions on the market which you can find with emitters like LEDs, but also with lasers. They all require lenses to achieve long distance, and on the other side you can have an avalanche photodiode, some CMOS sensors, a pin diode, something which is sensitive to light, but must be a fast sensor, because with such an approach, you're looking on the time of flight. So just to put it in perspective, if you want to have a resolution of only 15 centimeters, so half a face, let's say, you need to have a resolution in time of 1 nanosecond. And this makes it a rather expensive solution, since electronics must be advanced for this one. Again, here for motion detection, it's not a problem to see short time differences in the signal, and only then you can talk about presence detection once you know what you would like to subtract the signal from. Ultrasonic sensors, time of flight is same principle, but you're using now the air as a transmitting medium for the sound. There you have a loudspeaker. It's required to have a horn, which actually, if you look at the details and the previous presentation, you will see there are a lot of requirements for this horn. So really look into the details if you're interested in this technology, and you will see that it has also many disadvantages, not only advantages. On the other hand, the microphone, to see the sound which comes back, and this ping can be measured in terms of time of flight, since the sound speed in air with 333 meters per second or so is significantly slower than light. The electronics can be much cheaper, so it's actually a better priced solution. But here again, if you want to have real presence detection, you need to see first motion. So somebody must step in front of the sensor, and then you can have subtraction of a difference of the background. You can look on the amplitude whatsoever. Microwave sensors, and I specifically write there, not radar, because microwave sensors are those ones which can be regarded as broadly accepted by the market in terms of price. And they operate with the simple solution where they look only for the mixture of the emitted and the received signal. So they emit with one antenna, the other antenna, they receive the signal, they multiply, subtract them, or divide the signal, and then they are looking on the modulated signal at the end, with the modulation corresponding to the speed of the object. So those sensors, for example, are sensitive to any motion, and really only to motion, not presence, especially when the person is moving towards the sensor. When the person is moving the same distance to the sensor, then the sensitivity is significantly lower. Then as an active sensor, you can also regard sensors which use the natural sunlight, but also illuminate the scene when it's dark with infrared LEDs. This bounces off the person, and then you have at the end a simple camera with feature recognition. And the feature recognition is actually one of the little solutions on the market which I would regard to be real presence detection, because you can look for features specifically, picture by picture. You don't need to subtract any pictures from previously taken ones, but you look for features which were, for example, by means of machine learning being extracted out of this picture. So let's come to the actual technical solution which we have to offer as Excelitas Technologies, and we're offering with a very huge success on the market. Those are passive systems. And you can imagine now, if you don't have the active component by itself emitting, because you become yourself the emitter, then you can have a very low power consumption. So if you have the application where it is required to have a low power consumption, then there's almost no way around passive infrared sensors. However, we're talking now about electromagnetic waves in the long infrared region, which makes it then technically a bit challenging to find, for example, transparent materials if you would like to look through a window, and also to have the sensitivity high enough in order to see us glimmering in the dark. Why I'm saying that we are emitting light? So this picture might seem to be a little bit difficult to understand, but I will take you through this because this helps you a lot then afterwards designing in such a sensor, if you understand the basic physics, the basic principles of physics. And the principle here shown is on the x-axis. So on the lower side, you can see a wavelength. So the wavelength of an electromagnetic wave, where you can see, for example, the rainbow colors corresponding to the visible light. The visible light, or the light visible to the eye, is between 400 and 700 nanometers. And then we come to the one. The one is then 1 micrometer up to 10 micrometers. Please notice it's a logarithmic scale. So 1, 2, 3, 4, 5, 9, 10, and then it goes up to 100 micrometers. Then you see on the left side something which looks very complicated. This is something like the energy per room segmented per the wavelength, and then you have something which is the power of something. So just understand this scale as, for example, the probability to get a photon from the object given a certain temperature in this particular wavelength. So let's have a look, for example, if the object of interest has a temperature of 32 degrees C, you can see on the right side a curve which has its peak around 10 micrometers. So a person with 32 degrees C is peaking around 10 micrometers. When you go to the left, the probability to see light significantly drops, because here again we have on the y-axis a logarithmic scale, and it drops even to almost zero, around something like 2 or 3 micrometers. So this gives you already an important background knowledge about the properties of materials which are allowed to build, for example, windows and lenses in order to enhance the product itself later on. Those materials are actually quite limited. So those are high density polyethylene, which is very established on the market. Polypropylene works as well. But things like glass, for example, even if you look for solutions which are quoted to be transparent in the infrared region, don't be fooled. The infrared region, which is sometimes referred to, is sometimes only for semiconductors. And semiconductors are near infrared, so around 1 micrometer. You recall maybe the LED, which was at 960 nanometers. So there you will find glass which is easily transparent to this wavelength. However, if you would like to detect humans, then you must have a material which is transparent around 10 micrometers. And then if you increase the temperature of the object, you will see that the probability to emit light in shorter wavelengths becomes bigger and bigger. And it's at a certain point, like given here in this example, where you have a curve around 1000 degrees, you will see that more photons are actually emitted where the red band is and less where the blue one is. So it becomes to glow red. And then you increase further the temperature, like the temperature of the surface of the sun has, so 6000 degrees C, and you will notice that there it is peaking around green. And now you can imagine why the evolution said, okay, let's have our eyes most sensitive to the green region. If you would like to detect this 10 micrometer wavelength, you have actually a bunch of technical solutions shown here. I'm going through this in the other presentation in detail. However, established on the consumer market are pyroelectric sensors and thermopiles, which are themselves thermal detectors. Thermal means that they are receiving the radiation, the light, on a surface of something, and they are being heated up by this radiation. And this heat up can be identified by means of currents, voltages, and resistance. So let's have a look on the pyroelectric sensors. This is the most common solution on the market still. You can see the solution consists of the multifocal Fresnel lens together with a pyroelectric sensor. Shortly, you can have a look on closer on this lens. This is actually a lens which consists of many small lenses, facets which are segmenting the room. Later on, you will understand why. But if you want to have a high sensitivity to motion, then to small motion, then you need a lot of those lenses. And then you can imagine the more lenses you have, then the less intensity you get per lens in a certain direction, and this again reduces the sensitivity to a distance. So talking about this multifocal Fresnel lens for itself would take another hour, which I will omit now. If you're interested in this one, we can have it in a separate talk. Maybe you can always contact me if you have any questions. However, the pyroelectric sensor looks something like that. On the right side, you can see there are actually two elements displayed, where they are on top a minus, 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 and then plus, plus, plus. So you can see there is something like charges which are separated. And then you have a second element where the charges are also separated but the other way around. This is because you don't want to have a sensitivity to temperature changes. And in this solution, you see by compensating one element with the other, you get the requirement to have a lens. So a pyroelectric sensor will only work properly when you have something like a lens or something which confines the field of view, where you force the person to be identified to be visible only on one of the two elements of the sensor. This sensor, you can see, can be regarded really like a battery. And this battery discharges once you stop moving. This means that this sensor can be regarded only as a motion detector, or at least, or at most, an occupancy detector, but those are not presence detectors. The problem with those sensors is today, for many devices, the Z height, which is required. On the one hand, the elements themselves have sizes or dimensions of at least 1 by 1 millimeter, square millimeter, typically for a dual sensor 2 by 1 square millimeters. So this makes the product itself already quite large in Y and X dimensions, but when looking on the total height of this device, you are limited by the lens, because the lens cannot simply be brought as close as possible to the elements, because the closer you put the lens to the sensor, and of course reduce the focal length because you want to have a sharp image. So the closer you put it there, then the wider the field of view becomes. You know it maybe from cameras. When you want to look into a far distance, you need to zoom in, which means extending the distance between the lens and the sensor. So today's system height is critical for many products. And you've seen there are actually solutions which are compact for thin, flat devices. However, they all consume quite a lot of power. So this is why we proposed to use a thermopile for motion detection. Why a thermopile? A thermopile itself works a little bit different than a pyroelectric sensor. You can see here a seebeck effect which is being used, which leads to thermoelectricity, which means when you use an N-type silicon leg combined with a P-type silicon leg and put one side to a warmer place than the other side, then you can produce actually a voltage. And this voltage can be measured. And such a thermopile detector, as you can see it on the left side, is a device which is thinned from the back side to have really good absorbance of temperature and a temperature increase which is significantly higher than the thermopile's bulk material around this sensitive area. Then you can see also there are legs drawn, so red, green, which are just those N-type, P-type silicon legs going inside and outside, all combined together into one thermopile with a total length of, let's say, several centimeters. With that one, this is nothing new, the thermopile. Thermopile was used until a couple of years, mostly only for remote temperature measurement. The nice thing about the thermopile is that the voltage is always there as long as you have a temperature difference between the membrane and the bulk. So you can connect then this temperature difference or the voltage as an output with the temperature of the actual object. And actually, Excelitas was, or the former, sorry, I forgot the name for it. So the former we were once named EG&G, or as you've seen when you look into our history. And at the very beginning, we were the first ones to come up with a solution for remote temperature measurement for human body temperature. You will also find our sensors in, for example, printers. Everywhere when you have something which is rotating, moving, it's difficult to connect an NTC to this object, but you would like to know the temperature of the surface of this object, then you rather use a thermopile to determine the surface temperature. Pyrometers also, same principle. But you can do more with that. So the CaliPile was introduced as a smart thermopile at the beginning. Of course, like everybody is requesting it, the first choice is then the SMD solution of this one. You can see it's very compact with 4.4 millimeters by 2.6 millimeters in the XY dimension, and the Z height is 1.75 millimeters. Very compact device. And now you need to do some processing, which is actually being implemented on the CaliPile itself. So everything what you can see here in this picture is implemented on the ASIC and is constantly running. So this part has no sleep mode, no hidden features, no cheating on the numbers. What you can see here is constantly being applied with a power consumption of only 50 microwatts. You will see it on the next slide. But what you need to do is, if you have such a tablet, like for example on the upper left corner, you have to distinguish from different objects. And one object might be, for example, a heat source, a constant or slowly changing heat source, be it a sun which is heating up a carpet, a window, or maybe it's a heater which is turned on, off, whatsoever. All those objects will provide you radiation, which will be seen by the sensor. And you need to distinguish this radiation from a person which walks by or goes towards the sensor. How you do it? We have only one channel available. You've seen a thermopile is in this case only a 1 pixel sensor. What can you do? You look the radiation which is being emitted by those objects is then a net radiation which comes onto the thermopile, and it consists of the person which approaches the sensor, and maybe the background, which is the sun which starts to shine, but also you have ADC conversion fluctuation, so simply noise. And all this must be taken out from the signal in order to have then the raw signal of a person which is approaching the device. So our solution for this one is we're actually separating one signal into two different signals, and one signal branch, the upper one, you can have a look. It's fed through a low pass filter, like for example with a cut-on of 8 seconds rise time, and this will filter everything out which is quickly moving or quickly changing. So for example, a person walking by will give you a signal which is quickly rising and falling, and this will be filtered out. And this can be regarded as the background which you don't want to see. So now you can see already one thing which is critical then. In order to have the sensor operating correctly, you must have knowledge of your background. And this background can be, of course, recorded with our sensor, and then we can have a look together on the background. For typical applications in home appliance or for indoor consumer applications, and a cut-on of 8 seconds rise time is already a good number to work with. But if you want to extend, for example, the distance or the sensitivity of the sensor, then you need to play with those numbers. This background you can subtract actually from a signal which still has the signal of the person which is approaching the thermopile. This signal by itself is also taken from the raw data, low pass filtered, with now, for example, a cut-on of 1 second rise time. And this cut-on will still leave the information of the person walking by. It will filter out the fast ADC conversion fluctuations, and then you have something like the filtered signal, which still consists of the signal of the person and the signal of the background, like the sun here. And then you simply take the difference between both, apply a threshold, and then the sensor can send you an interrupt to your host system once the threshold is exceeded or going below the threshold. So you see we have also implemented an interrupt feature, so you can put your device into sleep and then simply wait for the sensor to send you an interrupt to the host system and wake it up, which makes it really suitable for low power consumption applications. You might be interested in, of course, what distance can you achieve? Because I said it was aimed, or the target market is for solutions where you don't have space for a lens. Without a lens, you have already a wide field of view which are covering with the sensor. This field of view is specified as a signal or an amplitude as a function of the angle to the sensor. And if you look into the specifications, you will see we specified with 120 degree, and the specification says at 50% of signal. This 50% signal you can see here in this picture indicated as a red circle. And you can see also that the sensor which is standing here in this example is looking forward. So in the forward direction, you are receiving most of the radiation. And due to Lambert's law, when you go to higher angles, like here 45 degree, you are losing already 50% of your radiation because it goes with the cosine phi of the angle. Actually, this is a feature which is also visible to other sensors like photodiodes, or when you look on pyroelectric sensors and so on. So all those sensors have this dependence on the angle. And this is, for example, partially compensated by pyroelectric sensors by having larger lenses for large angles to collect more light. Just as a side note. Here we are concentrating now on the sensor without the lens. So what you can expect is once you have it set up, you can expect a sensitivity of up to 3 meters. And when you go to the sides, then the sensitivity goes down. You can see all this in a YouTube on our YouTube channel. Just put in there Excelitas Technologies, go on into the list of the videos, and then you will find a video about presence and motion detection, where we are illustrating what is happening. And in this video, you can actually see what such signals are looking like. So like, for example, here in this, you can see I'm standing in front of the sensor. You can see on the left side some graph showing values between 64,335 up to 64,375. So you can see there are 3 graphs in there. One in gray is the raw data of the thermopile. In green is the backgrounds, which is with a long pass filter being applied, and in red one with a fast filtered signal. And then you can see in the middle the raw data, how it is exceeding the threshold, and then you can say somebody was approaching the device. And yet this is only motion detection. So how comes that we are still referring to presence detection? And now comes it in handy that the sensor is permanently giving you a voltage as long as I am in front of the sensor. So I can go towards the sensor, the amplitude goes up. I can move away from the sensor, the amplitude goes down. So you can subtract further then this data from a constant background which you have applied to. So what you do is once a person comes into the field of view, you know the background, and then you apply this background value to the threshold of the sensor, and the sensor will then only give you an interrupt once the person, for example, is going away. Now comes the tricky part. You can see I've put here in brackets short time. And by short time, I mean it really depends on the conditions which you have. So like here, indoors, where you have a person in a home moving towards the sensor, and depending on the distance you would like to achieve, it is feasible to think of several minutes of real presence detection. After those several minutes, then it becomes difficult to see a non-moving object, because you can never make sure that the background, which takes most of the radiation, the whole room is radiating as well. This background might change over time. So those are details which we can discuss once it should be of interest for you. But please don't regard the CaliPile as a permanent presence detector where you think I can sense a person for sure for several hours when the person is not moving. Once the person starts moving a little bit, then you receive new triggers, and then of course you can extend the so-called presence detection. But this is something which can be discussed in detail. So the CaliPile can be regarded as an all-in-one solution because it has this integrated data pre-processing for presence detection and motion detection. However, of course, a thermopile just for presence detection would be simply too costly, so we implemented as well the well-known temperature measurement. So those sensors come in calibrated. And you can have an fast over and under temperature protection, because with time constants of below 30 milliseconds, you can have a very quick protection against over and under temperature by looking at the thresholds after processing, so the sensor can generate an interrupt. And as I said, only 50 microwatts at 3.3 volts supply voltage. Comes with I2C interface and so on. You can look up in the data sheet. And those 50 microwatts are constantly running data processing. So no sleep mode, no some active sensors, for example, can get also to very low power consumption, but this is only possible if they reduce the frequency where they emit their light or sound. So let's say you do it only once a second or once every 10 seconds, and then you go to sleep, then of course you can have also a very low power consumption. If you don't need a very responsive system, then you can be really happy with those sensors. But if you want to have something which is responsive, so really somebody which, like in this picture on the right side, should respond and display, turn on a display once you approach it, such a smart thermostat is an ideal proposal for the sensor, or a condition for the sensor, because it should display you more information. If you come closer to the sensor in a far distance where the amplitude is lower, you can actually distinguish also long distance and short distance with the sensor. You would like, for example, to have less information but displayed it larger. Yeah. And of course, you would like to have things like room temperature measurement. And room temperature measurement can be really significantly different from the temperature of the device itself, especially when you have a very high power ASIC or a microcontroller inside, which consumes a lot of power, heats up the whole device, and then you cannot deduce the room temperature from the internal sensor only. So you need to use then the radiated information into our sensor. I said also that the CaliPile is a family, and means the same properties you can find in different packages. Like for example, here the TPIS1T1086L5.5 is a lensed device. So with a silicon lens, you have a much smaller field of view, and it is much better to have only one temperature measurement spot, or you can use this device even like a light barrier, because you have a confined field of view. So you see only people moving through a very confined field of view. Is the CaliPile the solution? It's inexpensive, reliable if you set it up properly and understand the limitations of this one. And it gives you a high performance in terms of when you compare it to active sensors. Still, without the lens, you can have distances above 3 meters. It's EMI resistance, and the SMD package is approved, which can be an issue for solutions like pyroelectric sensors. Those are details which can be discussed separately. And you have real presence sensing, at least for a couple of minutes. So can the CaliPile actually, if you would combine it with a lens, replace a pyroelectric sensor with a lens? Let's have a look. So here the CaliPile in comparison with a digipyro, so a pyroelectric sensor, is shown, and you can see in the first line we have put here signal to noise. It's a relative number, so we put there a 1 for the TPS1S1385 and compare it, for example, to a quad element, so a sensor for the ceiling application with 4 elements, a PYQ1548. And this sensor is already 3 times more sensitive than the CaliPile. If you go to a dual sensor, it's even 10 times more sensitive. So the conclusion here is that the pyroelectric sensor with the lens is still preferable for a long range detection distance, unless you have something like a requirement that you would like to sense that somebody is in close proximity to the sensor, because with the pyroelectric sensor, it's difficult to distinguish between distances. You can do it a little bit with some algorithms, but it's significantly easier to do it with the thermopile. And as I said, the big advantage, not only the low power consumption, but also the total size of the system. So you can have it as small as 1.75 millimeters in Z height. For the pyroelectric sensors, you have always to take into account that you have to apply a lens, which from experience, for example, can have something like 15 millimeters. So the value for you, we would not sell such a sensor if we would not know the benefits of the sensor against other competition on the market. And those are here shown as one of the biggest value, or figure of merit, as I call it. If you plot here the distance which you can achieve with such a sensor versus the field of view which is covered by the sensor, you can see that the pyroelectric sensor and the lens together will cover a very wide field of view of easily up to 120 degrees with a long distance of more than 10 meters. So 20 meters is nothing unusual. This is why the pyroelectric sensor is so successful on the market, because one simple solution covers a large area. There is a competitive solution. This is the microwave sensor. Despite being a little bit more expensive, it has advantages, like, for example, as an active sensor, being able to look through walls. Yeah? So it can be an advantage. For some, it can be a disadvantage. So sometimes even for burglar alarms, you need to combine both the microwave sensor and the pyroelectric sensor into one device. And then we have the proximity sensors, which gives you typically something like 50 centimeters detection distance. There are some solutions on the market with more detection distance, but this comes always with a smaller field of view and a larger power consumption. Same with ultrasonic sensors. They are covering quite wide area. However, please look into the details if you would like to integrate something like that into your device. And then comes what we understand, how we position our CaliPile. The CaliPile closes the gap between the proximity sensor and the pyroelectric sensor. So you can achieve up to 3 meters, have a very wide field of view, and very low power consumption. The power consumption shown here, a pyroelectric sensor, you can get down to 15 microwatts. So due to the high processing power of the CaliPile, it's still 3 times more, so 50 microwatts with the CaliPile. But if you compare it to solutions like ultrasonic sensor or proximity sensors, be it even typical numbers which I find on the market, still we are at least 10 times better. And here you have something like the system size. So the smaller the device, the better it is. Nothing outperforms currently the proximity sensor with only 1 millimeter height. We are actually working on solutions for even more compact devices. However, looking on what we can offer to you, we have now 1.75 millimeters. The ultrasonic sensors need a little bit more. Against the pyroelectric sensors, as I said, require a little bit more. And the value, difficult to say. We know our own prices. Please don't look too much on those prices because they are really volume dependent. So for example, we are talking here about high volume prices, and the CaliPile pyroelectric sensor with $3 are of course significantly more expensive than the proximity sensor. So you will find it only interesting if you're really interested in low power consumption and possibly also the detection distance which you would like to achieve. So as a summary, I would like to give you the impression that we will not sell you anything unless we really know it is a good solution for you. So if you discuss, for example, technical solutions with myself, we'll go through all the requirements and find the best suitable solution for you. Because anyhow, even if you would design in our sensors and discover, oh, okay, there are other solutions on the market, you would not be happy with my technical support. So this each technology has a typical application where it performs the best. The CaliPile is extending the range of proximity sensors with the benefits of, like, for example, low power consumption of the pyroelectric sensor. And as I showed, the CaliPile has many applications. So not only motion and presence detection, where I focus today on this one, but you can have also CaliPiles with medical accuracy for human body temperature measurement, surface temperature measurement, but also for industrial applications. So don't be surprised that if you come to us with a different application than just motion or presence detection, that you will still be proposed a CaliPile for this solution. Okay, so thank you very much for listening. Now we think we are ready for questions. Oliver?
Yes, thank you very much, Prometheus. Interesting presentation and a nice overview of latest technology updates and how we can close the gap between long-distance motion detection with pyroelectric sensors and short-distance sensors, such as capacitive devices or proximity sensors. Yes, during the presentation, we received quite a few questions from the audience, which I'm going to present to you now for Prometheus' response. Prometheus, one question from the audience is that what are the limitations for the detection distance? Please.
Yes, so limitations, you can, like, often people ask us, can't you simply make a sensor which is more sensitive? In principle, we could. However, you will notice, as I've shown in the application, that the real limitation is not the sensitivity of this part, but it's the background. So those algorithms which we have implemented have a limited capability of suppressing this background, and the faster the motion of the person is to distinguish from the background, and the slower the background changes are, the higher the detection distance will be, which you can achieve. The other way around, if you have a very noisy condition, like for example going outside and you have wind breezes, maybe direct sunlight whatsoever, it will be difficult to achieve a long distance.
Okay, thank you, Prometheus. There is another question from the audience. Will the sensors withstand standard reflow processes, or do they need some special procedure?
Yes, I believe this question comes from the knowledge that pyroelectric sensors can depolarize if you go over a certain temperature. So, for example, if you take our TO-CAN sensors, they are not qualified for exceeding they're not qualified to exceed temperatures about above 200 degrees C for a long period of time, because then the sensitivity would go away and you would have a dead sensor. The thermopile, however, is a semiconductor, so the physical principles do not change even after a standard reflow process. So you can treat them like any other reflow component without any special care.
Oh, okay. Thank you very much, Prometheus. But now we are approaching the end of our time, and we'd like to keep everybody on their busy schedules. I'd like to thank Prometheus again for the presentation, and hope that you had very good information to see. For more information, please visit excelitas.com and feel free to visit our Contact Us page to submit any further questions or requirements you have for IR sensing technologies. Watch out for our post-webinar mail with links to related topics and this webinar's video. Thank you very much for joining, and I wish you a very nice day. Goodbye.